Good afternoon, everyone, and welcome to the University of Manitoba Alumni and Friends Virtual Learning for Life program Climate Series. My name is Tracy Bowman, and I'm the Executive Director of Alumni Relations and a very proud alum. Before we begin, I'd like to acknowledge that the University of Manitoba campuses are located on the original lands of the Anishinaabe, Cree, Oji-Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So thank you everyone for joining us from wherever you are around the world and making this event part of your day. As you may know, we're able to offer this program free to all of our alumni and friends around the world, thanks to the very generous sponsorship of our affinity partner, IA Financial Group. Many thanks to them. You can learn more about the insurance options that they offer to our UM alumni on our UM alumni website. So before we get started and I introduce our speaker for today, just a few housekeeping details. So if you've been with us before for our previous Virtual Learning for Life series, you will know all of these things. Today we are recording the session, and we do that so not everybody is able to attend live, and so we have this option so you can view it again and again. You can share it, and all of our Virtual Learning for Life sessions are on our UM Alumni website and YouTube, so we encourage you to look at that. We have many sessions over the last 2 years, so I really encourage you to look at all of those sessions on many, many different topics. Participant, you will know that the way that we ask our speaker your questions is there's two different ways. You'll see a chat function in YouTube. Feel free to use that and you can ask questions there. But we also use a platform called slido.com. And today's password for the date is VLFL6. And that way you can just ask your questions throughout the process. I monitor that site and we bring those questions up and we ask as many as we can. And if we don't get through all the questions, we'll make sure to forward those to Dr. Ali afterwards and see if she's able to answer them. But hopefully we'll get through as many as we can today. So now with that, I'm delighted to introduce today's presenter, Dr. Karen Ali, and she's presenting on the topic of The Future is Unstable, Studying the World's Great Ice Sheets and Glaciers to Understand Sea Level Rise. So Dr. Ali is an assistant professor here at the University of Manitoba in the Department of Geography, and her research is part of the large glaciological community effort to understand how the world's glaciers and ice sheets are contributing to sea level rise in a warming climate. She's particularly interested in ice-ocean interactions that hold a major control on the stability of the Greenland and Antarctic ice sheets and many smaller ice caps and glaciers. Much of her work has focused on the nature of melting beneath the floating ice shelves that fringe the Antarctic continent, which in turn modulates rates of ice delivery to the ocean. Her current interests, there are many, they expand many different areas, but they include processes at other ice stream boundaries like the calving processes that control rates of ice tongue retreat and ice shelf collapse, grounding line processes that change ice flow velocities and the impacts of the ocean-induced melting, and shear margin processes that control the stability of the grounded ice that feeds the ice-ocean interfaces. All extremely important topics that she'll be able to address to some point within the presentation. So she's very knowledgeable in this area, and I hope that you really enjoy this really interesting presentation. So with that, I'm going to pass it over to you, Dr. Ali.
Well, thank you so much for having me. It's a real pleasure to be here. I still haven't quite gotten over the fact that I can talk to people from around the world sitting in my office at home. So this is a great opportunity, and thanks for having me. So yeah, I'm going to talk today about the work that we're doing. Some really big picture questions is what I'm going to go for. So by the end of this, I'm hoping that you'll understand a little bit about what glaciologists do, how we carry out our work, and that you have a good kind of handle on some of the really, really important questions in glaciology that matter to people all over the world. So that's where we're headed today. We'll get the slide to advance. Okay, so sea level rise. Let's talk sea level rise before we get into the glaciology. I tend to call sea level rise a here and now problem. Now, in Winnipeg, it might not be quite, immediately a here problem, but this is an issue that affects people all over the world. And so we certainly feel the effects all over the world. I think that there's a tendency to think about sea level rise as being something that happens, it's going to happen in the future, right? There's this looming thing that we have to worry about, but it's not right now. It's coming in the future. And that's just not the case at this point. Sea level rise is absolutely a now problem. It's going to get worse in the future. We're going to see more of it in the future, but it's happening right now. So this is a high tide in Kiribati. This is not a storm. This is a pretty typical high tide in many places, on many islands. If we want to get a little closer to home in North America, here's a high tide in Norfolk, Virginia. There's places in towns now where they have signs for roads for low tide, and they've got signs for the boats that go through there at high tide. This one really gets me. This is a parking garage in Miami, and that is an octopus in the parking garage in Miami. Again, this is not during a storm. This was a particularly high tide when the sun and the moon are aligned to really pull those tides. But this is high tide. This is a normal kind of cycle that we have that's flooding structures that we built, assuming that they would stay dry. The effects of sea level rise are first felt in a really big way. They tend to be first felt during storms. So this is a picture of storm surge from Hurricane Florence. The idea is if you raise background sea level, when you pile up water against the shore during a storm, that background sea level is higher, so the storm surge is higher as well. It can go farther inland. We get more destructive storms from this. So this is not a future distant problem. This is something that we need to be thinking about right now and knowing that we are going to see more of it in the future. So let's get into some of the data on this. Looking at rates of sea level rise since 1880, there's a couple of different data sets that we're seeing here. Just to get you oriented, so the x-axis there is time. The y-axis is looking at the change compared to an average between 1993 and 2008. Basically, you can look at the trend and say, hey, sea level's going up. This is in millimeters that we're looking at on this y-axis. So you can see that, in the past 20 years or so, we've gone up, about 55 millimeters, 5.5 centimeters in global average sea level rise, something like that during that time period. So it seems really small, but when you keep doing this year after year, and when you notice that this trend is kind of curved upwards, and we expect that curve to continue, that starts stacking up and starts really, really mattering to coastal areas. The reason that we're seeing sea level rise, there's a bunch of different components that play into this. One of the big ones has actually been thermal expansion. So when you warm up the oceans, the water takes up more space. It expands when it gets warmer. So some of the sea level rise that we've been seeing has been because of this thermal expansion. And for a while, that was one of our biggest contributors to sea level rise. A couple decades ago, that was something really major. But it's been pretty quickly outpaced by simply adding new water to the oceans. Water that was on land, that wasn't taking up space in the oceans, and is now taking up space in the oceans. So you're seeing here this black line and the purple line here, when we got some more data, is showing you, okay, this is what we've measured for sea level rise. And then these are the components that we're estimating based on lots of different methods. And if we add them together, we ought to get that black line. And that's that purple line we've added together. So we're pretty good at this. We're pretty good with our observations. They match really, really well. We know where this sea level rise is coming from. So most of it is coming from adding water. And that water, it says there, it's mostly meltwater that we're adding to the oceans. Specifically, we are melting the world's glaciers and ice sheets. And that's where our biggest sea level rise contribution comes from. Now, I'm not going to talk a lot about like mountain glaciers, smaller glaciers that we'd find in Canada. That's something we're certainly studying, and I'm going to refer to some of the processes that we're studying on those glaciers. But we're going to mostly stick to the bigger players in the game today. And our big players in this game, when it comes to adding meltwater to the oceans, our big players are our two ice sheets. So we have the Greenland ice sheet in the northern hemisphere and the Antarctic ice sheet in the southern hemisphere. And I like looking at them on this map and thinking about, look at this huge map of the world, seeing how much of our world is covered in oceans. Those oceans are what we're seeing, get higher over time. And we have this little Greenland ice sheet up here, right? It looks pretty small on the map. I'm a glaciologist. I've been studying this for a while. I've been to Greenland. I've been to Antarctica. I've stood on the ice sheets, and I just can't quite wrap my mind around just how much ice is packed into those small looking ice sheets on the map. Greenland, this ice sheet right here, if we were to melt all of the ice in Greenland, sea levels around the world would go up by about 7 meters. Just think about that for a moment. Looking at all this ocean all over the world, if we melt just all the ice sitting on this landmass right there, everything goes up 7 meters. It's huge. There's a tremendous amount of ice that we're dealing with, and that's Greenland. This is Antarctica. Antarctica has 57 meters of equivalent sea level. There is just an unbelievable amount of ice sitting in Greenland and Antarctica. So when we're talking about right now, those, 5 centimeters, whatever it's been in the last 20 years or so, seems really insignificant when you start thinking about how much ice there is available to add to sea level. Now, I do have good news for you, which is that we are not in danger of melting all of Greenland and Antarctica anytime soon. That is a really, really slow, long-term process. There's certainly been times in Earth's history when there has been no big ice sheets on Earth. But certainly on human timescales, we're not going to melt all of Greenland and Antarctica. But when you're talking about 57 meters of sea level equivalent sitting in Antarctica, it doesn't take a very big percentage to be doing things that matter to the whole world. There's a tremendous number of people who are living within a meter of sea level. And so a very small percentage change in Greenland and Antarctica means a really huge change in impacting people's lives. So we're going to get into some details. I'm going to mostly focus on Antarctica today because it's the biggest player in this. But before we dive in, I want to give you just kind of some very broad background on, okay, we know these are big players. We know these matter to sea level. What do we do? How do we study these? How do we figure out what's happening there and what's likely to happen in the future? And there's kind of 4 big ways that we go about it. So one of those ways is through remote sensing, and that can take a bunch of different forms. I'm mostly talking about satellite remote sensing. When I talk about remote sensing, there's also airplanes and drones are involved in this. We also have underwater vehicles that would count as remote sensing. This is a little video of one of our relative, well, it's not that new now, it's been up for a few years, ISAT-2, which is up orbiting the Earth, sending little green laser beams down to the surface and measuring how long it takes for those to come back. And using that, we can get an idea of ice surface height. We do all sorts of different kinds of remote sensing measurements. We actually measure gravity, which directly tells us how much mass is in the ice sheets pulling on the satellites as they orbit the Earth. We take satellite images that look a lot like our normal pictures that you're used to taking with a camera. We can learn a lot from those. We also take pictures in wavelengths that we can't see with our eyes, infrared, radar, that sort of thing. We can make 3D surface models using some of these pictures. So this is a huge way when you're thinking about ice sheets that cover entire continents, having something that can be orbiting the Earth and taking full pictures below it is really, really helpful. It's not the only thing that we do, of course. Satellites can't do everything. Satellite sensing can't take continuous measurements, right? So we can't have, if we go to the field, we can put an instrument down that takes measurements of that location continuously over time, whereas the satellites are orbiting. So there's long time periods where they're not taking measurements from a given area. Satellites can't see underneath the ice or within the ice. Satellites can't measure the shape of the bed that the ice is sitting on. Satellites, we can get some pretty high resolution data from satellites at this point. But if we want real extreme details, we got to get in there and do it ourselves. So we do a lot of field work as well. In situ measurements means in place. So getting those measurements helps overcome those limitations. And we can then put satellite measurements together with field research to get a much more complete picture of what it is we're seeing happening. We combine these with laboratory analyses. So there's all sorts of really interesting stuff going on in laboratories, particularly with ice cores, looking at chemistry, physics of ice, the crystal structure, all those details. That's not something that I've been involved in a lot, but I certainly benefit, the work that I do benefits a lot from that detailed understanding of work that's being done in laboratories. And then we put it all together. We put it all together using numerical models. So numerical models are basically just sets of equations that computers are solving for us. So we're using statistical relationships, but largely when it comes to ice at least, we're using physical equations that actually describe how ice flows and how ice breaks, that sort of thing. And we try to put it all together and calculate how things are going to change in the future. So we take all of those observations that we got from remote sensing, that we got from field work, that we got from doing laboratory analyses, and we try to recreate those with our equations. And if we can recreate our observations pretty well, then we can have some confidence that we can run it into the future, predict what conditions might be like in the future, and see how our glaciers and ice sheets respond. So those are kind of the four things that we need in order to put all of this together. And I'm going to touch on several of these. I'm going to mostly talk about the field research and remote sensing aspects today, because that's mostly what I'm involved in. But we need all of these pieces to really be able to understand what it is that ice sheets are doing and likely to do in the future. So I said we're going to return to Antarctica. Antarctica, 57 meters of equivalent sea level. It's the biggest player in the game, and it turns out it is changing really, really rapidly. So it's if you want to choose one place that we need to study right now, if we're going to understand sea level rise, Antarctica is not a bad option. Here's what's happening in Antarctica. I'm going to show you an animation. I'm going to kind of walk you through what this is showing, and then we can go back through it so you can take it all in. This is from the NASA's Scientific Visualization Studio. They do amazing work. And so what you're seeing on the left, in this graph over here on the left, we're moving forward through time on the x-axis, and we have mass loss on the y-axis. So as we see these lines go down, we're seeing the ice sheet losing mass. This is actually being measured using gravity, asking satellites how hard the ice sheet is pulling on those satellites as they orbit the Earth. So it's a direct measurement of mass change. So that's showing you the trend over here. And then the colors on the map are showing you where that mass loss is taking place. So red means losing mass. Blue actually means gaining mass. So you can see those colors there. And as we watch this animation again, we see this progress. We see there's a few different hotspots where we're losing a lot of mass in Antarctica, but you'll notice there's one area in particular that is losing mass like crazy compared to the rest of Antarctica. And this is known as the West Antarctic ice sheet. So Antarctica is divided into, not really in halves, but in two, by the Transantarctic Mountains. So that's a mountain range that runs through here and goes up through the Antarctic Peninsula. And we call everything on this side East Antarctica, and the bit on this side, West Antarctica. So we can see that East Antarctica is pretty stable. There's a few spots, this is the Totten Glacier catchment, that we're seeing a lot of loss. We're seeing places where it's actually snowing a bit more, so we're getting some mass gain over time. East Antarctica is pretty stable. The action right now is in West Antarctica, in this area over here, where we're seeing this huge mass loss going forward over time. So that, of course, begs the question, why West Antarctica? What's going on in West Antarctica that's causing it to be losing so much mass over time? And it really comes down to the shape of the seafloor and the way that the ocean is influencing it. So this map is a little bit hard to wrap your mind around when you first start looking at it. So what we've done is we've put Antarctica mostly in gray down here. So this is the coastline of Antarctica. It's this box over here. So we see Antarctica mostly in gray. We put floating bits of Antarctica in light blue there. So this is the coastline of Antarctica in West Antarctica. And the colors out here are the depth of the seafloor. So we see there's deep ocean out here, and then we get up onto the continental shelf, the shallower areas near shore. And those are in the yellow colors. And you'll notice as you come from the deep ocean towards Antarctica into those yellow colors, you'll notice some spots where we go back to deeper, light and dark blues in these areas, kind of blues and greens. And those are deep areas. We see these kind of deep troughs that come in from the edge of the continental shelf, aiming towards these floating bits of West Antarctica. There's a bunch of them over here. And what's going on here is that during the past, we've had times when there was a lot more ice on Earth and Antarctica expanded and glaciers actually advanced over the continental shelf. And wherever glaciers flow, they tend to carve into the ground, and they carve troughs. And they did this over many glacial cycles of advance and retreat. And so they've carved themselves these troughs that go over the continental shelf. We also have in this area of West Antarctica, and this is just kind of based on how ocean circulation works, there's a warm water mass called circumpolar deep water that exists usually off the edge of the continental shelf. Now I put warm in quotes. You wouldn't want to swim in this water. It's a few degrees above freezing. It's certainly enough to cause a significant amount of ice melt, but it's not very warm for human terms. Don't go swimming in circumpolar deep water. But it is warm enough to melt the continental shelf, or melt the glaciers as it comes onto the continental shelf. So what's happening is these troughs are kind of directing circumpolar deep water in this area is pushed up onto the continental shelf. And it's a pretty dense water mass because it's very salty. So it basically just flows downhill into these troughs, and it directs it right at some very important ice masses in West Antarctica. So we've got the warm water, but there's another piece of the equation that's really important. So now we're looking at a map of Antarctica as though we've taken away all of the ice and we've just left the bed. And again, we see kind of reds and yellows are shallower, or they're higher land masses in this case. And these blues and greens, if you look at the color bar, those are negative numbers. So anywhere you're seeing these kind of green into blues and into these deep blue colors, that's actually land that's sitting way below sea level. This lowest one down here, 2,800 meters below sea level, is what we're looking at. So if you look over here in West Antarctica, again, there's the Transantarctic Mountains. So East Antarctica is over here. You can see why East Antarctica might be pretty stable. It's sitting up on big, thick, old craton. It's sitting way above sea level. But West Antarctica, even though it's sitting on land that is way below sea level. And what that tends to mean, there's some more complicated math that goes into this, but what that tends to mean is as the water comes in, the warm water comes in, and it causes West Antarctica to melt back, as it melts back, there's even more ice for it to get in contact with because it's getting thicker as you go inland, and that water can continue to flow in, continue to interact with the West Antarctic ice sheet, and we end up with a very unstable situation. So this is why West Antarctica is changing so fast. We've got warm water, it's got access to the ice, and we've got ice that is grounded way below sea level, which allows it to continue affecting it in a pretty rapid way. Now, we're going to talk about one particular glacier, Thwaites Glacier in West Antarctica. If you were to argue what is the most important glacier in the world, of course, I'd argue that there are lots of important glaciers in the world. But if you were to argue which one's the most important, you'd probably end up at Thwaites Glacier. Thwaites Glacier holds back a lot of the ice that's sitting in West Antarctica. So there's that bed map we were looking at, and Thwaites Glacier on this outline is right here. So it's sitting right at the mouth of this really deep basin, holding back a whole lot of the ice in that really vulnerable area of West Antarctica. Thwaites Glacier may be in what we call an irreversible collapse. Now, be careful with the term collapse. Collapse is fast when we talk about glaciological timescales, but it's slow for human timescales in the way that we use the word. So when we say that Thwaites Glacier, it may be in a collapse situation, we're still talking about something that will take many centuries to happen. We'll see there is, the process happening much, throughout that time, but the full collapse of Thwaites Glacier would take several centuries to happen. It's still holding back a lot of sea level. This still matters. Remember, so West Antarctica as a whole holds about 3 meters of equivalent sea level. Thwaites Glacier doesn't control quite that much of it, but it's controlling a major part of it. So once again, even a small percentage starts to matter a lot when we're talking about retreat. So this irreversible collapse of Thwaites Glacier, we hope that it's not an irreversible collapse, right? We're doing our best to model it. There's some projections that show really, really scary results. You don't need to worry too much about these maps over here, but look at these 3 maps. These are what's going to happen in 2500 if we curb our fossil fuel emissions, if we burn it kind of typically the way that we've been doing, or if we burn everything we've got. And that's showing you how much ice will be left in West Antarctica, assuming that we have those scenarios. And you'll notice those 2 right there, kind of typical burning, or maybe a little bit more than we are now, and burning everything we got. By 2500, we're losing a significant amount of West Antarctica. So the question is, are we committed to this at this point? Is this collapse truly irreversible? And that's the question that we don't quite have an answer to. It might be at this point. It might be something, and I'll talk a little bit more about why in a bit, but it might be something that we can't turn around at this point. Thwaites Glacier is going, and it's going to retreat all the way back to the Transantarctic Mountains. But we might not have yet crossed that line. If we turn things around, if we curb fossil fuel emissions, if we keep warming from going too high, we might have a chance yet of stabilizing Thwaites Glacier. So we're doing our best to figure that out. I am very lucky to be part of the International Thwaites Glacier Collaboration. This is work mostly between the US and the UK. I moved here from the US, so this is with some of my colleagues there. Some other countries, Sweden, Germany, South Korea are all involved in this. I think I may be the only investigator currently living in Canada. There might be a couple others, but it's really a privilege to be part of this. And what we're trying to do is really answer those questions. Is Thwaites Glacier unstable? What's going to happen with Thwaites Glacier? And we've got 8 different teams that are working in different ways, that are really trying to do the field research, the remote sensing, give some historical context to all of this, and then put it all together into numerical models to try to understand what Thwaites is likely to do. I'm part of the Thwaites Amundsen Regional Survey and Network team. We love our acronyms. We're the Tarzan team. And so we're really interested in understanding what the ocean is doing around the fringes of Thwaites Glacier. We've had a ground-based team this is actually from the 2019-2020 field season, this picture. We also have people who have been working from ships to try to make measurements so that we can all compare them. We were on the floating ice shelf of Thwaites Glacier. I've mentioned this term before, but basically these are the floating extensions of the ice sheet. So they're still attached to the ice sheet. They're part of the ice sheet, but they're truly floating on the ocean. They just kind of float off the edge of the continent. They actually go up and down with the tides, although it's not something you can feel when you're on it. So there's a kind of view of an ice shelf, and what we're really interested in, we're thinking about what keeps an ice shelf stable or unstable. We need to figure out the ice flow, and we need to also figure out what the ocean is doing underneath. So ice shelves end up being really important for a bunch of reasons. One is that they're really early indicators of change because they're interacting very closely with the ocean and also being affected by ice sheet dynamics. They tend to be some of the first things to change. They also matter directly to sea level rise, not because an ice shelf itself will raise sea level because it's already floating in the ocean. It's kind of already taking up space. but they tend to run into islands and the edges of bays and things like that. And by doing that, they help hold back the ice behind them. So if an ice shelf falls apart, the ice on the continent can flow faster into the ocean. So we need to understand ice shelf stability if we're going to be able to predict that sea level rise. Atmosphere interaction also matters to ice shelves for sure, but it's not so much on thwaites. When we're talking about thwaites, there's not much surface melt going on. Mostly the driver of change is that ocean and the ice dynamics behind it. Doing a lot of field work for this. Working in Antarctica is challenging to say the least. So I was down there for this 2019-2020 field season, and we went down, mid-November, we got to McMurdo Station. This is the big US base down here at the edge of the Ross Ice Shelf. McMurdo Station's pretty cool. You can see it's big. There's like 1,000 people living there during the season. We got to McMurdo and we got stuck there for about 3 weeks extra. We had some time to get field equipment ready anyway, but there were about 3 extra weeks of delays for at least part of our team because of weather, because of difficulties with airplanes. So we got stuck there for 3 weeks. Finally got out, and the first thing we did was we flew to Waste Divide, which is an old drilling camp in the middle of the West Antarctic ice sheet. And this was kind of a chance for us to take all of our gear, which we had on these big pallets, and break it down into smaller pieces so we could put it on smaller airplanes to take down to thwaites. We got to Waste Divide and promptly got stuck for another week at Waste Divide, again, because of weather delays. So at this point, it's been a month that we're trying to get out to the field. We did get a few people out in the field before we got out, before the rest of the team made it. But we did finally make it down to Thwaites Glacier. So there's a picture of the camp as we were flying in, or maybe that was when we were flying out, I forget. At any rate, we had on our team, there were 11 of us that were working in the field together. We lived in tents. It wasn't too cold. It stayed not too much below freezing most of the time that we were there, which was pretty nice. We're pretty close to sea level, so it wasn't too cold, but the tents actually heated up quite nicely on windless days. We had 24 hours of sunlight while we were there, so it meant we could work really long days to try to make up for all those weather delays. This is our mess tent, so you can see the whole team kind of crammed in. We all had our nice spots to sit in the mess tent. It's Martin up doing some cooking for us that day. Spent Christmas on the ice sheet, so there's our Christmas dinner. We got frozen veggies. That was a big treat for Christmas dinner while we were out there. It's hard work. We were very lucky to have not much in the way of storms while we were there, which was really nice. This is the beginnings of the only real blow that we had while we were there. You can see the snow blowing across the ice sheet. And you got to be a little careful because you can get big drifts that sometimes can overwhelm tents depending on how things are organized. And we were trying to move one of those drifts, and one of our teammates accidentally snagged a hook from a snowmobile on the side of our mess tent and gashed a giant gash in the side of the tent. So that's a picture of me. So we spent 3 hours trying to sew up the tent to keep it together during the storm while we had teammates holding it together on the outside and 3 of us sewing on the inside. And so that was an adventure. So it's certainly a very challenging place to be working. Here's some of the ways we got around. So that is Erin Pettit. She's our PI for the Tarzan project. This is an LC-130. So it's a big Hercules airplane on skis, which they use to get us up to Waste Divide. Once we got our gear reorganized from that, we put it into a basaler to get us down. This is flown by Ken Boric Air. It's actually a Canadian company. And this basaler actually, they've gutted it. It's like all new equipment inside, but the body of this airplane was actually part of the D-Day landings during World War II. So we could really use some new airplanes in Antarctica. This is a Twin Otter, a smaller airplane, also on skis that we used to get around. And then most of our work was on snowmobiles when we were out on the ice. So what is it we were doing? We were out there trying to figure out if Thwaites is falling apart and why. So we did a few different things while we were there. One was active seismics. This is Atsumoto from Temple, who was in charge of this. What he's doing there is putting a string of small explosives down a hole that we've drilled. And he's got a string of sensors. They go all along. It's about a 0.5 kilometer long wire that's connecting all these sensors. And we had to dig holes to put I mostly worked with Otsu while I was out. Had to dig holes to put all the sensors in, and we'd set off the explosion, and we would measure when the sound waves bounce back. And that can tell us about the shape of the seafloor underneath the ice, as well as getting us the ice base. We also did a lot of ice penetrating radar. So this is Erin Pettit's setup. We didn't have many snowmobiles to go around. So she ended up walking her radar a lot of ways. I think she walked like 190 kilometers during the field season. I took it out for a day. It's no joke walking. I don't know, what did I walk? 15, 18 kilometers that day in, giant snow boots. Fortunately, it was pretty packed out snow, pretty easy surface to walk on. But that gives us a picture of what's going on inside the ice. We drilled 2 holes through the ice sheet. It's not a drill the way you might think about it. It's a hot water drill. So we're literally squirting hot water into a hole until we get all the way through the ice sheet. And that allows us, Martin Trufer, who was in charge of from Fairbanks, who was in charge of our drilling. And that allowed us to put some really cool instruments in. So these are the Amigo stations, and I should remember what that stands for, but I don't. Basically, in that hole, we put a whole bunch of instruments down through the ice to measure what the ocean is doing underneath the ice shelf. And we also had a weather station on top. We installed 2 of these Amigo stations while we were out there. It's Ted Scambos from Colorado. He's in charge of those Amigo stations, working on it before it got set up. And we've had those out there now since that 2019-2020 field season. We did get a team back to service them this past season. I told you all about the delays and difficulties we had during our field season. We got 5 weeks in the deep field, something like that, when we were out. This year, the team got 3 days after all of their delays. So unfortunately, we've got one station that's not really sending us data back anymore, but we were able to recover a lot of it. And we hope to get out next year to get some more of these data back as well. This is all combined with, so we take all these field observations and we combine them with a lot of remote sensing data, as I'd mentioned before. This is a video, and I'll run through this a couple times so you can see what's going on, because it takes a minute to kind of get your eye in on what you're seeing. This is Thwaites Glacier that we're looking at. Over here, this is grounded ice, so that bumpy stuff is where it's sitting on land. And out here is the floating ice shelf. So our main camp was about here on the Thwaites Eastern Ice Shelf when we were out. And what we're looking at is about 20 years of changes on the Thwaites Glacier ice shelves. You'll notice back in 2002, when this image is from, there's a huge ice shelf over here, as well as the one we were on over there. And you'll notice as we scroll through time, that ice shelf just kind of falls apart. We lose the Thwaites Western Ice Tongue, is what it's called there. And in the meantime, we can see really big changes going on the Thwaites Eastern Ice Shelf. So for example, if you watch this kind of middle area that looks nice and smooth back in 2002, you'll notice that as we get forward in time, we start to form giant cracks in the middle of that area. You can really see them coming out right at the end there. We're also seeing big changes up here. There's an island that it runs into up there that it's interacting with. So we're seeing extremely, extremely rapid changes on the Thwaites Eastern Ice Shelf, on this area we're trying to study. It's a lot to kind of put together with all these data to try to understand what's going on. We're working very actively on doing that. Some kind of big picture things that we found: extremely complex basal melt patterns. The ocean conditions, one thing that's really challenging about them is that they change really quickly, both in space and in time. We're seeing that change on the Eastern Ice Shelf. And what we've kind of come to a conclusion on just in the last few months, based on looking at these observations, understanding our data, and thinking about what models show, is that Eastern Ice Shelf, that part where we've got instruments on, will probably not be there in the next several years, maybe as few as 5 years. It's probably not decades that we're looking at, but this is still a very, very difficult thing for us to predict with a lot of detailed certainty on the timing there. So hopefully that gives you some idea of what we've been doing, why we've been doing it, in terms of this kind of big picture of what matters to sea level rise in Antarctica in this case. But I want to step back just a little bit bigger as I start to wrap up here, and think about, okay, so what in general, what are we trying to answer still? What big questions are still facing glaciologists around the world? And these are the kinds of questions that we need to answer on thwaites. We for sure need to answer on thwaites because it's the one that matters most in these predictions. But as you've also seen, thwaites is really hard to work on. It's really hard to get to, and it's not, an easy place to be able to get measurements and to answer these questions. And there's still a lot of fundamental questions that we're trying to answer that we can study in other places. So we'll be doing some work on a glacier on southern Ellesmere Island this summer, because it's a lot more accessible, it's smaller, so we can see the whole processes a little bit easier, and hopefully we can get at some of these questions there. We're asking the same questions on smaller glaciers all over the world. We're asking the same questions in Greenland, and certainly asking these questions in Antarctica. This one really mostly still pertains to Antarctica. This is this idea of the marine ice sheet instability. So this is what I was talking about when I said, okay, as West Antarctica retreats, it gets thicker as you go inland. The more it retreats, the more ice is in contact with the ocean. And that's not a stable situation, right? So if it retreats and then more interacts with the ocean, and that makes it retreat, and then more interacts with the ocean, we get a positive feedback, which kind of increases that process and continues that retreat. And that's where I say, okay, we could have pushed it over a tipping point. We might be at a spot where that dynamic instability kicks in and there's not much we can do about it because it's just not stable. This is something that the basics physics is very well understood. We know that this process exists. We know that this feedback exists, but we don't know a lot about the pace, right? Trying to figure out the answer to that question of, well, how quick is sea level rise going to come? City planners need to know that. We're not very good at knowing that pace yet. And so the two ways we're really addressing this question are through field studies. So a lot of the stuff that we've been doing is getting the data we need to help us understand what that pace is likely to be. And then numerical models. So we don't have observations. We've never seen a marine ice sheet instability take place in any large scale in the time that we've been measuring. So we really have to rely on numerical models to understand how this instability might play out in the future. There's actually a second of these scary positive feedback loops that might kick in, and again, makes a huge difference to how quickly this kind of retreat might take place. And that's called the marine ice cliff instability. And to get you an idea of how new some of our understanding is, so the marine ice sheet instability, middle of last century, we had a pretty good idea of the marine ice sheet instability. We had a pretty good idea that West Antarctica was the vulnerable spot where this might happen. Marine ice cliff instability, it's been closer to a decade of study of really understanding the marine ice cliff instability, although some other professions, geomorphology, for example, had some of the fundamental physics down already. Basically, what happens in a marine ice cliff instability is if you get a cliff of ice that's just too tall, it gets to a point where it just falls off. I mean, that's basically the whole thing is ice can only support itself to some height. We see this in rock cliffs. There's kind of a maximum height that rock cliffs can get to before they kind of fall off. And so the marine ice cliff instability is if we get an ice cliff that's too big, because, for example, we have a marine ice sheet instability that's causing retreat into thicker and thicker ice, we could get to a point where the ice cliff just kind of falls off. And that will make it so that retreat happens much more quickly. This is another thing that we're really mostly relying on numerical models to get a handle on this. We're certainly making detailed observations of the way that ice breaks and how that continues over time. But this is, again, something we've never seen on a large scale. So we have to really work on our models to understand, again, how that affects the pacing. Sea ice is another one. There's lots of people here at the University of Manitoba working on sea ice around the world. there's actually some really interesting sea ice glacier interactions that might change the pace that that ice cliff failure might be happening. So this is something that we can work with a little bit more directly through our observations, particularly through remote sensing. We can look at, for example, thickness and ice extent of sea ice and look at how glacier retreat happens with and without sea ice in different parts of the world. And then, of course, the numerical models come into this as well. So that might be something that stabilizes ice cliff retreat or slows it down a little bit. Fracture processes are huge. This is something that is really, really difficult to model in detail because it takes a tremendous amount of computing power. So again, we're relying a lot on observation still to understand just how ice breaks and how quickly it can break and how big those fractures tend to be and what sort of chain reactions that can set off. So there's lots of different situations, lots more things we need to know about how those fracture processes take place. And finally, the last one I'd put on that list, the details of ocean forcing and basal melt. So, again, we're trying to measure thwaites itself. We've got instruments underneath the ice shelf. We've got our other half of our team doing ship-based work, measuring ocean temperatures and circulation. So we're trying to figure out what's going on at thwaites. But then exactly how that plays out, exactly the small scale nature of those melt processes that set the pace that those processes occur, how those melt processes interact with the fracture processes that we were just discussing. There's a huge number of questions that remain in that as well. So this is something we address through every kind of large category that I talked about of investigation when it comes to glaciology. We're making ocean measurements using our radar and actually underwater vehicles to look at the details of the bases of ice shelves and the fronts of calving glaciers. We're doing lab experiments to see how melt rates proceed. We're using a lot of remote sensing for this. And of course, then again, the numerical models that come into it. So I hope that gave you an idea of what it is we're doing, why we're doing it, and why this is something that we as humanity, as people around the world, need to care about. There's still a tremendous amount that we don't know when it comes to these kinds of questions. There's a lot that we do. We're learning more every single day. We're pretty sure, for example, that West Antarctica is retreating. But there's a lot of questions within that. Shouldn't say pretty sure. We're absolutely sure that West Antarctica is retreating. But there's a lot of questions within that about the pace that will occur in the future that we're still trying to work on. So with that, I will leave you, as we say, with some gratuitous charismatic macrofauna. These are Weddell seals that we saw early in the season at McMurdo, and those are Adelie penguins. You're not allowed to approach the Adelie penguins, but I was sitting on a pier watching this group of penguins way out, taking pictures of them, and there's one other guy with me, and he goes, "Oh my gosh!" And suddenly this whole group comes swimming right in front of us and jumped out like 2 meters in front of me. So those are the Adelie penguins there. Thank you so much for having me. I'd be happy to answer questions.
Wonderful. Well, thank you very much. That was really fascinating. And the fact that you get to see animals like that in their natural habitat, which most people do not get that chance to, is pretty amazing. I'm a penguin fan myself, so those are beautiful pictures.
I spent a lot of time waiting for the flight out of McMurdo looking for penguins.
Yeah.
So, yeah.
Okay, so we have had some questions come through Slido and through YouTube. So just a reminder to everyone, now is your chance. If you have some questions, please do make sure that you ask Dr. Ali, and we'll be checking both of them. So I'm going to go to YouTube first. And one question that we've received is, isostatic rebound has affected water levels in the past. Will continued glacial melting result in ocean level increase due to isostatic rebound?
So isostatic rebound is certainly in all of our sea level predictions. That's included in the projections that are happening. So isostatic rebound, for those of you who don't know, basically when you put something really, really heavy on a continent, like an ice sheet, as that ice sheet melts, the continent, or as it exists, the continent is pushed down underneath it. And so as the ice sheet melts, the continent very slowly pops back up. And that happens over thousands of years. So it's a very slow process. And so as we've had ice ages in the past with big ice sheets sitting, for example, on Winnipeg and all of North America, it's pushed the continent down, and we're actually still experiencing that land popping back up over time. When it comes to affecting sea levels, the most important effect is not about the land and the ocean rising and taking up more space because the ice sheets were mostly on land. So it's really about the land, the continents rising. And what that tends to mean is there are actually in many places in the world, including much of the coastline of Canada, although not all of it, that is actually experiencing relative sea level fall. So the land is popping up faster right now than sea levels are rising. So there's actually some relative sea level fall in some places where there were recently ice sheets. We're seeing that in Greenland and Antarctica too, that as they melt, we do see some isostatic rebound very slowly from that, but there's still big ice sheets there, so we're not seeing as much of that. So mostly that kind of stuff comes into predicting how it's going to impact individual areas of coastline. It's more about the local relative changes when it comes to isostatic rebound.
So then do you have more erosion as a result of isostatic rebound?
Not so much. I mean, you have more land that's exposed to, rain and other surface processes, but certainly not on the same time scale. The isostatic rebound happens a lot more quickly. We do worry about coastal erosion. Certainly in the Arctic, we worry about coastal erosion, but a lot of that is because we're thawing the permafrost, the frozen ground that's underneath the land near the coastlines in the Arctic. And so that makes them much more vulnerable to coastal retreat along with sea level rise in some places.
Okay, very interesting. Okay, so I'm going to go to Slido now, Teddy. So just wanted to make sure that we're there. Okay, so first question: the added water to the oceans from melting ice sheets would greatly affect the salinity of the oceans. Are the effects on sea life understood?
Well, I'm certainly not a biologist, so that's an area that I have much less expertise in. When we're talking about these changes, so to humans, a few meters of sea level rise is huge. It matters tremendously. When you think about average ocean salinity, that doesn't globally have quite as much impact because there's so much ocean water sitting underneath it. But locally, where we're actually around the ice sheets, where we're actually melting that ice and dumping fresh water into the oceans, we certainly do see a lot of changes because of that salinity. I don't know the details of what that's doing to sea life in the area. I do know that it's changing the way that sea ice forms. So it's a little bit easier to form sea ice when you have fresher water. On the other hand, it's much harder to form sea ice when it's too warm for sea ice to form. And it's certainly sea ice has major impacts on wildlife as well. So I'm afraid I don't know the details of that, but I would say on a global scale, it's not a huge change, but locally there's probably larger impacts on local ecosystems because of those changes.
Okay, great, thank you. Next question from Slido. Teddy, if you want to pull it back up again. And that is, how does the timing of the ice melt fit into past glacial interstadial periods, 12,000, 24 to 25,000 years ago, etc.?
Yeah, so if I'm understanding what we're asking here, so I've mentioned these past glacial advances and retreats. So there were times, as the questioner said, like 20,000 years ago, that there were many, many big ice sheets on Earth, including covering most of North America, a lot of Siberia, a lot of Europe were covered by ice sheets. And that retreat really happened, the last glacial ice sheets in Canada were 11,000 years ago, 12,000. It depends where you measure retreat, depends on where you work because it retreated slowly over time. So certainly we've had that big change in the past. The changes we're seeing now are kind of a new pulse. And there's been some other pulses as well. So we had a cool period in kind of the 1800s for a little while where things even kind of re-advanced a little bit. So we've had some kind of wiggles as we've come out of that. But basically, we had retreat. It was stable for a while, and now we're retreating again is kind of what we're seeing. So there's a pretty separate set of changes that we've observed between that glacial retreat from the last glacial maximum, to what we're seeing today since human warming has really come into it. I hope that answers that question.
Okay. No, thank you for that. Just put another plug out to everyone for questions on YouTube or Slido. I know a topic that often comes up, it's sort of a comment / question for myself that I know we hear a lot about. I mean, here in Manitoba, we hear and talk a lot about polar bears having Churchill in our province and the unique climate that is Churchill for those of us who've been able to be lucky to go there. And so last week's presentation focused on precipitation in the Arctic and, rain versus snow and how, and she also didn't go down the path a lot about how it impacted polar bears, for example, but we hear things, in the news or from whatnot from climate scientists about, polar bears having to go further out to get food, and is there enough ice for them, and how they're impacted in their own climate. So I don't know if there's anything you're able to comment about polar bears specifically with regards to sea ice.
Yeah, so one thing to be clear on first, and perhaps I should have led with a little bit of this background, is that sea ice is completely different from the glacial ice that we're studying. So sea ice is ice that's formed directly out of seawater. So if you put a glass in the freezer, it forms ice on the top. And if you put an ocean in the freezer, it forms ice on the top. So that's what sea ice is ice that's formed directly out of seawater. And it has its own set of, we know a lot about sea ice. There's been some really tremendous work over the last many decades, particularly once the satellites, really came into play in the last several decades of really understanding what's going on with sea ice, why it's changing. Still lots of questions to answer. So Arctic sea ice is decreasing very rapidly, particularly in the summer. We're seeing less and less sea ice, and that's really what affects things like polar bears, is that there used to be much, much more sea ice cover than there is now in the Arctic. We're actually not seeing the same kinds of big trends in the Antarctic, and that comes into some of the question on salinity there. There's this kind of fight between things warming up and the water getting a little fresher that can kind of, fresh water makes it easier to form sea ice, warming makes it a little bit harder. Antarctica is a lot more separated from kind of the rest of the world because it's completely surrounded by ocean. And so it's got kind of its own thing going on there. Glacial ice that we're talking about, that forms from snow originally. So it's land ice. It's snow that's piled up over time to the point that it's compressed to ice. So they're completely different. And certainly when we're thinking about polar bears, when we're thinking about communities that rely on hunting on sea ice in the Arctic, the glaciers actually have a much smaller impact on this than the changes in sea ice on the things that communities and ecosystems really care about, particularly in the Arctic. Certainly on a global scale, when sea ice melts, it's already compensated for because it's floating in the ocean, so it doesn't raise sea level rise when sea ice melts, but the land ice does. So we've got two kind of different types of ice that matter for very different reasons.
Mm-hmm. No, I'm glad you pointed that out. Those of us who aren't climate science, after you explain it, that makes very good sense. Land versus sea ice.
Exactly. I should have started with that. Yeah.
No, thank you for that. A question just came through with Slido, and that is: does recent earthquake movement, less than 6.0 magnitude in the South Sandwich Islands, been taken into account?
So I don't know, specifically about these earthquakes. Certainly, when it comes to predicting sea level, we're using a really complex network of really, really precise GPS stations all over the world. And so those are measuring the land movement in great detail so that we can see in comparison how the ocean movement is changing in relationship to the land. So I don't know about those earthquakes in particular. Earthquakes, really big earthquakes can cause a few meters of movement. In land, usually it's tremendously smaller than that. But overall, those kinds of changes are measured in that really, really detailed GPS network so that we can understand how the land is changing in relation to the ocean.
No, that's interesting. Good. That was a good question. Another one just came through on Slido, and that is: we hear about impacts to coastal areas, but what about impacts to interior locations? Mm-hmm.
So the direct impacts are certainly on coastal areas, but what it does to interior locations in terms of sea level rise specifically is displace large populations. So we have, as I said, just a tremendous percentage of the population is living within a meter of sea level. So this is the kind of level that we're going to see displaced populations within the next century or so, with how close many of these areas are to sea level. I went to Cancun a few years ago, and there's like these gigantic hotels like right on the beach, right next to the ocean, and it just, oh man, it's not going to take much for those to change. So what happens then is when you have change that's affecting large populations on the coastline, they have to move somewhere. And so we certainly have the direct economic implications of destroying communities on coastlines. And then we also have the indirect economic implications of people moving to new locations. Probably, I mean, just as importantly or more importantly with that is that many of the communities that are really close to being affected by sea level rise now and will be in the future are underserved communities that don't have a lot of resources, that often don't have a strong voice in the governments and the groups that could be helping them to move. And so they often don't get very much attention. And so there's major human rights considerations as we change our climate, as we change our sea levels, about which communities this is really impacting.
Okay. Well, thank you for that. It's 2:00, and I think we got through all of our questions. So thank you very much for all of that clarity and clarifying all those various different things and the really interesting work. And so I think before I close, I'll just say, Dr. Ali, is there any last comments you wanted to say, or anything about your research going forward, or something else that you're working on right now, or the next time you're going to be back in Antarctic?
I guess I would just say, this is scary stuff. I live in this really weird world, because when you see change as a scientist, it's exciting. We get to see how things work. We get to learn all these interesting things because they're changing. But as a human, every time you see change, it's terrifying. It's sad. And it can be really difficult to kind of think through all of this material and realize the kind of changes that we're causing to our planet and what that's going to do to human communities. So I think the message that I'd want to leave with is that we do still have some control over this. We're not sure we've pushed thwaites over the edge yet. And so there's lots that we can do in terms of personal choices, in terms of political choices, in trying to promote the kind of change that will stabilize thwaites and other glaciers in the future. So don't give up hope yet. There's a lot more that we need to learn, but there's still a lot we can do.
Well, I appreciate that. I think, every little bit helps. All of us have a role. All of us have a purpose in terms of protecting our planet. So thank you for that. So as I mentioned earlier, before we began the presentation, this is being recorded. So we will share that with you in an email in a day or so. We'll also be having a follow-up survey. So please do share your feedback. It's the only way that we're able to improve, and that you're also able to share your feedback on other presentations. Of note, we developed this climate series because of the feedback that we received from all of our viewers, that we created the 6-week climate series. So thank you for that. So we do look at your feedback. So I do encourage you to respond to that survey and let us know what you think. So next week, if you haven't registered for next week's session yet, I encourage you to go on our website and do that. Next week's presenter is Dr. Nicole Wilson. She is a Canada Research Chair in Arctic Environmental Change and Governance, and also assistant professor. And she's with CEOS, or Center for Earth and Observation Science, and the Department of Environment and Geography. And she will be speaking on the topic of decolonizing climate justice and water governance in the Canadian Arctic. So we'll be returning to the Canadian Arctic again next week. So stay tuned for that. Again, if you have not registered, please do go on our website, and you're able to do that and register for that, and the next 2 sessions to follow from there. So thank you again for participating today. Please check online for upcoming and past sessions, so you're able to take a peek at those. Look at our website for other opportunities and activities that we're hosting for all of you as UM alumni and friends. And thanks very much, and we will see you next week.